Well, good morning, pre-calculus students. We're ready to move on here to our next video, which is still on ellipses. This will actually finish our section on ellipses. So we're going to look at the application of ellipses. And let's go ahead and let's get started. So ellipses, that shape, actually describes a number of significant things in the world around us. Probably the most significant thing is it actually describes the path of the orbit of celestial bodies. So for instance, the orbit of things like the Earth around the Sun, the Moon around the Earth, other planets around the Sun. These are all following elliptical paths. And so if we want to understand the path, we have to understand ellipses in their nature. So let's look at this. So first thing we have to do when we go to apply these is we have to be able to get the standard form by completing the square. So let's look at how we're going to do that. So first, here's number 45. And what I'm going to do here is I'm going to walk us through the process, and I'm going to indicate what I'm doing on the right. So the notes on the right side here are going to be what to do. And this is a review of completing the square. This is not something that should be brand new to you, but we have to do it for two different variables now. Where with parabolas, we only did it for the one term that was squared. Now both terms are squared, so we must do it with both. So the first thing that we're going to do is we are going to do this step here, which is going to be to group like variable terms. So basically what I list here, this is the instructions that I did to go from the first line to the second line. So notice what I did. I put the x terms together. So here's the x squared with the other x term. I put the y squared with the other just singular with a linear y term. And I moved the constant term to the right of the equal sign. So that's grouping like variable terms there. Next thing that I do is I factor the leading coefficients for each separate type of variable. So notice here with the x terms, I factored the leading coefficient was a 9, so I factored a 9 out of this one. And here I factored a 4 out of this one. So notice I kept the parentheses here so I could distribute it back in and get back to this. Kept the parentheses here, kept the 23 over there on the other side. Next step is now we will actually complete the square. So what we're doing here is actually completing the square. So I take half of the -2, which is -1, square it. -1 times -1 is +1. Put the +1 in. Take half of this 2, which is 1, square it, put the +1. Now, when I've added this in, since this is all inside the parentheses multiplied by 9, I've really added 9 to this left side. And when I put this 1 in here, since it's multiplied by 4, I've really added 4 to this left side. So I also have to add a 9 and a 4 to the right side. Now I can go ahead and write it as squares. So I can write it as the x minus 1 squared and the y plus 1 squared. And notice now I'm getting very close to standard form, but I have a 36 over here after taking the 23 plus 9 plus 4, and I need to have a 1. So I will divide both sides by 36. That will get me, and I distribute it into each term here, that'll get me my 1 over on this side. So there is my standard form. Now I can easily pick out and answer things. Notice my a squared is actually here because this is the bigger one. Okay, so my a squared becomes 9, my a becomes 3, my b squared is 4, so my b becomes 2, and then I can use my Pythagorean relation to get my c, which is radical 5. My c squared would be 5. So my center, I can pick out my center. My x coordinate is 1, my y coordinate is -1. My eccentricity I can figure out because I can take my c over a, so that's radical 5 over 3. So this one here is actually quite eccentric. It would be quite oblong in its shape. Very non-circular. The vertices, I can go from my center and I can add and subtract a. In this case, it would be vertical, so I would add and subtract that from the -1. So I have 1, 2 if I add 3 to the -1, and 1, -4 if I subtract. The foci, I must add and subtract the radical 5. So I have 1, -1 plus radical 5, and 1, -1 minus radical 5. So that's finding all the significant features after getting it in standard form. Okay, let's look at another example here. So here's another example where we're given an equation in this form here. Once again, since we need to have a 1 over here, we will divide through by 4. Notice though, this gives us something a little bit different. When I divide through by 4, this gives me 9 over 2 times this x minus 2 squared, and this gives me a 3 over 2 times this y plus 3 squared, and that's equal to 1. Now, the problem is this really isn't the form that I like to see it in. So what I'm going to do is, notice, multiplying by 9 over 2 is the same thing as dividing by 2 over 9. And multiplying by 3 over 2 is the same thing as dividing by the reciprocal 2 over 3. Now I can see much better what my a squared and what my b squared would be. Notice in this case the a squared is the bigger one. 2/3 is actually bigger than 2/9, so this is another vertically oriented parabola. So I know that my a would be the square root of 2/3. B is going to be the square root of 2/9, which is actually the square root of 2 over 3. And notice this one is bigger than this one because this one's denominator, the numerators are the same, and this one's denominator is smaller. So if you divide by a bigger denominator, it's a smaller number. So now that's how we would do one like that. So I'm just showing you, don't panic if you get something here where you have something in the numerator where your fraction here is bigger. You can always move it down in the denominator by dividing by the reciprocal, and then you get it in the denominator and you can analyze it from there. All right, another skill you have to do, another application is if you have a graph, how to get an equation. So let's look at a graph. Here's a graph that we're given. And the essential things that we have to get when we go to do an equation, we have to know whether or not it's a vertical or a horizontal situation. So we have to know whether or not the a squared goes under the x term or the y term. And we have to know our h, our k, our a, and our b. But these are pretty easy to pick out here once we have a center. There's our h and our k, so we know our h is -2, our k is 1. We can see that it is further horizontally than it is vertically, so we know this is a horizontal ellipse, so we know that the a squared will go underneath the x term, and we know the b squared will go under the y term. And now we just find the distance. So from -2 to 1 here, that's a distance of 3, so I know my a squared will be 9. My a is 3, my a squared will be 9. My b has a distance of 2 going from 1 to -1, or going from 1 up here to 3. It's going to have a b of 2. So now I can go and I can so I know to grab my horizontal equation, and now I can just fill in. So filling in, there's my a squared, there's my b squared. And I've filled it in, and I've got my equation. All right, last thing when we look at applications are going to be orbits. So we have some terms we have to learn when understanding orbits. And there are some interesting things with regard to orbits. One of the things that's interesting when we go to do this is we always want to place the center of the orbit at 0, 0. We want it to be easy. Well, the easiest thing to do is have h and k in our formula is 0. That means as we look at a formula like this, and usually we will also always make it a horizontal ellipse. That's just easier usually to look at. So we'll usually always have it of this form right here. But once h and k are 0, then it's really easy. Then it's just x squared over a squared and y squared over b squared equals 1. Because we can place the center wherever we want to. We can orient it however we want to as far as that goes. Now, the trick to remember is the orbited body is not at the center. The orbited body is actually at a focus. So when I look at this, this is the situation I'm going to get. Now, I would listen to my description and then probably pause the video to sketch down what you see here. Notice the situation that's going on here. What we see is that the orbited body I've drawn here, that's at the focus. The distance between the center, which is known as hk here, which should be 0, 0 in most of our cases, that's c, the distance between the center and the focus. A is our distance from the center to a vertex, but the distance from the orbited body all the way out to a vertex, that long distance, notice that's a plus c, we call that the apogee if we're talking about the moon around the Earth, or we call it aphelion if it is a planet around the sun. Notice here helios for sun, and this term here refers to the moon. And then if we talk about the short distance, it's perigee if we're talking about the moon, or perihelion if we're talking about the sun. So some important terms to understand there. So notice perigee becomes the distance a minus the distance c. Apogee becomes the distance a from center to a vertex plus c. So with that in mind, you'll be able to figure out the application problems that you'll find. So it's going to be 8.2, it's going to be 46 through 50, and then 53 through 56, and this is all of these problems here. So go ahead and take a look at those. And if you do have questions, we will have a Zoom session today at 12:45. So, and I will post that along with join information. So hope things are going well. Stay healthy, and we'll see you in the next video tomorrow.